Hey everybody, Dr. A here, and in this video we're going to be exploring an example of using Castigliano's method to analyze a truss. In particular, we're being asked to compute the vertical displacement of joint C using Castigliano's method. We're also being told that all members have a cross-section area of 0.000625 meters squared and a modulus of elasticity of 190 gigapascals. So let's take a look at the truss we're being given here. So here we have a truss with 6 bars, and we have joints A, B, C, D, and E, okay? The height in the vertical direction of the truss is 2 meters, and each bay of the truss is 1.5 meters. And then the joint we're really interested in is this joint out here, joint C, which has 8 kilonewtons hanging in the vertical direction pointing downward, okay? So we're looking for the vertical displacement of joint C right here, all right? Now, before we actually get started with all of our calculations, the first thing we need to do, and this is good practice for us, is to show that the truss is statically determinate, okay? It's always good to double check that for ourselves and make sure we're not, thinking something is determinate when in fact it's really indeterminate or vice versa, okay? So the first thing to check for the determinacy is we want to look at the number of members, okay? We have 1, 2, 3, 4, 5, 6 members. So I'm going to say M equals 6. And then I'm going to say the number of reactions we have. We have 4 reactions because we have an external pin at A and at E, which generates 4 external support reactions. And then how many joints do we have? Well, we count the joints. 1, 2, 3, 4, 5 joints. So J equals 5. So what we say is we compare M plus R, and we see that that gives us 10. And we compare that to 2J. So I'm going to put a comma here. I'm going to say 2J, and that also equals 10. So since M plus R equals 2J, we have a statically determinate truss, okay? Also, there are no collapsible mechanisms for this truss, okay? So this is statically determinate. I like to remind ourselves of how to do this because some people have the misconception that just because you have 4 external reactions here, right? You got 2 at A and 2 at E. You have 4 external reactions. That means that you have a statically indeterminate system. But that's not the case. Remember, to investigate determinacy and stability of trusses, you are adding the number of members to the number of external support reactions, and you're comparing that to 2 times J. This 2 comes from the fact that you have 2 applicable equilibrium equations at each joint. So it's good to remember this fundamental concept. So now that we remember that and we have a statically determinate truss, let's get started with applying Castigliano's method. What do we do in Castigliano's method? Well, we apply a variable virtual force at the joint of interest in the expected direction of displacement, okay? So our joint of interest here is joint C. And if you look at the real load, this 8 kilonewtons, it's pointing down, okay? So that should tell us that the expected direction of displacement of joint C is what direction? Well, it should be expected to displace down. So I'm going to say plus P here. Okay, so now what we do for Castigliano's method is we analyze this entire truss by applying P plus 8 kilonewtons at that joint of interest, point C, okay? And so in this particular method, we are keeping the real load present at joint C, okay? So we're gonna have the virtual variable load with the real load both applied to this system, okay? So now that we have applied the virtual load here and we have the real load on there as well, the first thing we need to do is get our capital F forces. And we're going to do that by using method of joints. So we're going to say use method of joints to get our capital F forces in terms of that variable load P. Okay, and so if you remember your method of joints process, we're going to start where? Well, we're going to start at a joint where you have at least one known and at most two unknowns. So I'm going to start at joint C. I'm not going to go through all of the nitty-gritty details of method of joints because we should remember that from our basic knowledge of statics. So this is joint C. And we have FCD here, and we have FBC, and we have this angle here. This angle is given as the arctangent of 2 over 1.5 meters, so 2 meters over 1.5 meters, and you should get that that's 53.13 degrees, okay? And so here we're gonna say, it's just method of joints, sum of the forces in the y direction equals 0, and I'm gonna say FCD times the sine of 53.13 degrees minus the quantity P plus 8 kilonewtons equals 0. I do a little bit of rearranging and I get FCD equals 1.25 P plus 10 kilonewtons, okay? So that's our first capital F force in terms of P. Then I'm gonna say sum of the forces in the x direction equals 0. And I'm still looking at that same free body diagram. And I'm gonna say negative F BC minus that quantity 1.25 P plus 10 kilonewtons. Watch that negative sign. You're subtracting that entire quantity. And then we're going to say times the cosine of 53.13 degrees equals 0. And then we get FBC equals negative 0.75 P minus 6 kilonewtons, okay? So that is, we can go ahead and, use some check marks here. I'm gonna check off CD and BC, okay? So we have those two members. What next? Well, if you look closely, you should recognize that member BD is a zero force member, so we can go ahead and zero that out. You need to, if you're rusty on your zero force members, go back and look at the criteria for visually identifying zero force members, okay? Now, also again, by method of joints, which I'm not gonna get into all the details, we can immediately go ahead and say, well, we know what FAB is. Well, how do I know that? Well, again, if we were to look at a free body diagram of joint C, okay, we recognize that we had a zero force member here. We recognize that this was FBC, and this force over here is FAB. And so just by observation, we know that FAB should be equal to FBC, which is negative 0.75 P minus 6 kilonewtons, okay? So that's FAB. We checked that off already. Where do we go next? Well, if you remember your method of joints, we really should not go to joint A next because we have too many unknowns. We have 3 unknowns. You have the 2 external reactions and you have this member force. And you need to move to a joint where you at most have 2 unknowns. So our best option is going to be joint D. We have at most 2 unknowns. That's FAD and FDE, and we do have something we know already. We know FCD from a few minutes ago, okay? So I'm gonna come down here and I'm gonna say we're going to joint D next. And so I'm gonna draw a free body diagram of joint D, and remember we have that zero force member there that I can just kind of sketch there. and we have 1.25 P plus 10 kilonewtons hanging out there. That's from earlier. We have this unknown force FAD, and then we have this unknown force FDE. Okay, and we have the same angles theta all here. Okay, so we're going to say sum of the forces in the y direction equals 0, and we're going to write negative FAD times the sine of 53.13 degrees. I'm going to wrap this equation around here, minus the quantity, 1.25 P plus 10 kilonewtons times the sine of 53.13 degrees, all equals 0. We do a little bit of algebra and we'll get FAD equals negative 1.25 P minus 10 kilonewtons, okay? And then we're gonna use our next equilibrium equation, sum of the forces in the x direction equals 0. And we're gonna write negative FDE plus the quantity 1.25 P plus 10 kilonewtons times the cosine of 53.13 degrees. I'm going to wrap this equation around here and say plus the quantity 1.25 P plus 10 kilonewtons also times the cosine of 53.13 degrees equals 0. And I do a little bit of algebra, rearrange, and say FDE equals 1.5 P plus 12 kilonewtons. Okay, now again, I went through this method of joints pretty quickly. I did show my work, but if you're rusty on your method of joints, pause the video, rewind it, watch it slower, and do some intermediate algebra steps here that I might have skipped, okay? It's okay if you're rusty on method of joints. It might have been a little while since we've done it last, but this is just regular method of joints. The only thing you got to be careful about is you have this P floating around inside of your free body diagrams. So you have to be very careful when you're bundling these expressions together and you have negative signs sprinkled around there. You have to remember to distribute your negative signs appropriately, okay? So let's keep rolling along. At this point, we are ready to set up our Castigliano table, as I like to call it. And, you don't have to write a table like this, but I do think it is good to help you stay organized. So I'm going to make a column of the members, okay? And we're going to write all these down. Member AB, BD, DE, and AD, okay? And then I'm going to write the length of each member, all right? And, the diagonal members are 2.5 meters long. We got a couple of these guys that are 1.5 meters long. We got one that's 2 meters long, another 1.5 meters, and then 2.5 meters there. And then I'm going to make a column F as a function of P. These are these force functions. So I'm going to be very nice and organized and write all these down. And I know, it's a lot of writing, but again, it's better to spend an extra couple of minutes writing things down and hopefully get the problem completely correct rather than trying to rush and not be very organized and then making a lot of mistakes. So we got the last one here, minus 1.25 P. minus 10 kilonewtons. Okay, now Castigliano's method tells us we need to take the partial derivative of these force functions with respect to the variable load P. So here I'm going to make another column. I'm going to say dF dP, okay? This is a partial derivative with respect to P, which means that P is the variable that we're taking a derivative with respect to. So these partials will come out as 1.25 minus 0.75, minus 0.75, 0, 1.5, minus 1.25. okay? Now we need another column of F when P equals 0, all right? And so this is just going to be those constants out there, 10 kilonewtons, negative 6 kilonewtons, negative 6 kilonewtons, 0, 12 kilonewtons, and negative 10 kilonewtons, okay? Now we're just about ready to wrap up. Let's see if we remember Castigliano's formula, okay? Castigliano's formula says that the displacement of a joint, in this case, it's the vertical displacement of joint C, so I'm going to say delta VC, is going to be equal to 1 over AE times the summation as I goes from 1 to 6 in our case, because we have 6 members, of F dF dP times L, okay? Now, let's make sure we understand where this comes from. Why did I pull the 1 over AE out of the summation? Well, in our problem statement at the very beginning, we said A and E are the same for all members, okay? So because all members have the same cross-section area and E value, modulus elasticity, we can pull that out of the summation. If you have a problem where A or E is different for each member, you can't just pull it all out of the summation like I did here. You need to incorporate an A and an E column somewhere into your table, okay? But for our problem, it was kind of simple. We have the summation as I goes from 1 to 6 because we have 6 members. And then we have this product here, capital F times dF dP times L. So watch what I can do here. I can make a column here of that product, F dF dP times L, okay? And what I can do now is I can multiply these things together. So I can say F times dF dP times L, okay? And I can compute that product and make my last column. So when I do that for each one of these, I get, for the first one, I get 31.25. I get 6.75. I get another 6.75. I get 0. I get 27. And I get 31.25 again. Okay, so if I were you, maybe pause the video and punch these through and make sure you get the same number as me, okay? Now watch this. I can sum all of these together. I can add these numbers together vertically, and when I do that, I get a number. I get 103, and guess what? That is this summation right here, okay? That is that number. Now, what are the units of this? Okay, notice I haven't put the units yet. What are the units of this? Well, let's think about it. F, when P equals 0, has units of kilonewtons. dF dP is unitless. Okay, that's a rate of change of a force with respect to a force. So that's unitless. And then L has units of meters here. So I get units of kilonewton meters for that value of 103. Now, what does that mean? Does that 103 kilonewton meters, is that a moment? No, that is not a moment. That is a type of work or energy, okay? Remember, Castigliano's method is like virtual work in that this is energy-based, okay? This is about storing energy in members, okay? So this is like the definition of work or energy that we learned way back in Physics 1. That's what the meaning of these units are, kilonewtons times meters, okay? And so here I can substitute these values in, and I get delta VC is 103 kilonewton meters in that numerator, all divided by AE. Now, my A value was 0.000625 meters squared, and my E value was 190 gigapascals, but I need to take that to kilopascals. Why do I need to take that to kilopascals here? Well, it's because my numerator has units of kilonewtons times meters. I have to get consistent units, okay? So when you crank all of this through, you get 0.000 867 meters. Okay, and it's positive, right? It's a positive number here. And so remember, when your value comes out as positive, what does it mean? It means that your displacement is in the direction that you pointed the virtual force P. Okay, so if you had a negative, if this popped out negative in a problem, in a different problem, for example, that would mean that that joint is displacing in the opposite direction that you pointed P. So the fact that this was a numerical positive here, and this 103 was positive as well, means that our displacement was in the direction that we placed P, which was down up at the in our original figure. Okay. Now, this is a small number in meters. What you could do is, if you had a problem that asked for specific units, you could repackage this as 0.867 millimeters down, or you could repackage it as 867 micrometers down. The reason why I'm kind of emphasizing these different unit options is because if you're getting ready for the FE or the PE exam, they love to make sure you understand units. And so they'll ask you for a value or an answer of something in a particular kind of unit. So you need to be able to convert units quickly on things like the FE or the PE exam, or maybe a quiz or a test that you have in your class. Okay, so that concludes this video. Hopefully you found it helpful. If you liked this video, please hit like and subscribe, and thanks for watching.